In this set of videos, we're going to look at a series of calculations that we'll make use of in chemistry. First thing we'll look at is how we can convert from formula units or molecules, that is functional units of chemistry, to atoms. This is review for many. If we were to look at formula units, which we use as a term when we're speaking about ionic compounds. For example, if I took regular table salt and I wanted to deduce how many types of atoms and how many of each are in a single unit or a single formula unit of sodium chloride, I'd be able to say that there was, of the number of atoms, there's one sodium, there's one chlorine, for a grand total of 2 atoms. Slightly more sophisticated, aluminum sulfate. We've got 3 types of atoms to account for here. In the case of aluminum, you'll notice the subscript 2, which applies only to the aluminum. I have a subscript that's implied for the sulfur. It's an implied subscript of 1, which means we have 1 sulfur. Oxygen, we have a subscript of 4, so 4 oxygens. But we have a subscript after the closed bracket, which applies to everything that's inside those brackets, which means, in fact, we need to multiply everything in there by 3. So suddenly this 1 sulfur became 3, the 4 oxygens was actually 12. This gives us a grand total of 17 atoms in 1 formula unit of aluminum sulfate. But the same applies when we look at molecular bonding and a molecule. So we use this example of carbon dioxide. When we look at how many atoms are in that, we've got 1 carbon and 2 oxygens, a grand total of 3 atoms. In this video, we'll determine how many particles are in a mole of a given substance. It's commonly referred to as Avogadro's number, sometimes referred to as Avogadro's constant. We know that Avogadro's number is a very large number, 6.02 times 10 to the 23. That means that there are 6.02 times 10 to the 23 anything in a mole of that same thing. For example, if we looked at a mole of gas, a mole of hydrogen gas, there would be 6.02 times 10 to the 23 H2 molecules. We would have 6.02 times 10 to the 23 carbon atoms in a mole of carbon. We'd have that many donuts in a mole of donuts. So to go from particles to moles, we need to divide by 6.02 times 10 to the 23. If we're going from moles to particles, we would actually multiply by 6.02 times 10 to the 23. So if we're talking about formula units, if we're talking about molecules, if we're talking about atoms, the exact same thing. A mole of something can be converted to a total number of particles of that same thing. The unit, be it atoms, molecules, formula units, must be the same in both cases. So how many atoms are in a mole? Well, it really depends what the mole of substance is you're talking about. It's not a direct route from one to the other. We actually have 2 steps to this calculation. For an example, if we were to ask how many atoms are in a mole of carbon dioxide, you'll probably remember that carbon dioxide has 3 atoms in it. So we'd have to come up with an equation that would combine a few different steps here. We've got 3 atoms for every molecule of CO2. We know that there's 6.02 times 10 to the 23 carbon dioxide molecules per mole of carbon dioxide. And we're asking a question that says how many are in 1 mole. So we have 1 mole of carbon dioxide. Once we cancel out all the units, we find out that the grand total is 1.81 times 10 to the 24 atoms. We did that by canceling out CO2 molecules and CO2 molecules, mole of CO2, mole of CO2. and then it was just straight math. Determining the molar mass is pretty straightforward. Obviously, we'll need to make use of a periodic table. For the next few examples, we've used rounded numbers. To determine the molar mass of sodium chloride, grab a periodic table. We find that NaCl, which we know has 1 sodium and 1 chlorine. Sodium has a molar mass of 23 grams per mole, chlorine 35 grams per mole. So 1 times 23 is 23, 1 times 35 is 35. Add those two together, gives us a grand total of 58, which means 58 grams per mole is the molar mass of sodium chloride. When something's got some subscripts in it, we need to make sure we account for those. So in the case of ammonia, we have 1 nitrogen at 14 grams, and we have 3 hydrogens at 1 gram, which gives us a grand total of 3 grams per mole of hydrogen, a grand total of 17 grams per mole, the total molar mass of ammonia. Converting mass to moles is pretty straightforward. We just need to make use of that molar mass that we've learned to calculate. Going from mass to moles, we divide. Going from moles to mass, we multiply. This actually is a very simple equation that we can make use of. Looks like this. N represents the number of moles, and the unit of that would be mole. The lowercase m represents the mass of the substance, which is in grams. The uppercase m stands for molar mass, which the unit would be grams per mole. If we were to calculate the mass, we just rearrange that same formula, and it would end up giving us mass equals number of moles times molar mass. Here's an example. If we were to determine the number of moles of sodium chloride in a 116 gram sample of sodium chloride, keeping in mind we have already figured out to calculate the molar mass, and that was 58 grams per mole. So if we were to go ahead and write down what we know and substitute into the equation, we determined that we had 2 moles of sodium chloride.